Hi everyone, I would like to welcome all of you to Frontline Systems webinar on an overview of simulation applications in Excel using our advanced products. My name is Dr. Sima Maliki. I am Consulting Lead and Modeling Specialist at Frontline Solvers. During this presentation, if you have any questions or comments, please type them into the chat box to be answered at the end as time allows. I strive to remain within the promised time frame, yet to thoroughly cover all the material, sometimes it takes a few minutes longer. I very much appreciate your cooperation. As we all know, the Monte Carlo simulation and risk analysis techniques are widely used across many industries and functional areas. Here you can see just some of the examples: energy and utilities, chemical, manufacturing, transportation, financial services, or different applications such as retirement planning, pricing, forecasting sales, and so on. That is because almost every business outcome has some uncertainty. Uncertainty can impact our decisions and actions in desirable as well as undesirable ways. If you own shares of stock, the future price is uncertain. It may go higher, which is desirable, or it may go lower, which is undesirable. Furthermore, you might be concerned with future demand for your product, production variations, delivery lead time, or future interest rates. The main point is that when there is significant uncertainty, expected case or average estimates are typically wrong. When you have multiple uncertain factors affecting your business situation, what-if analysis is very likely to be insufficient. That is because it won't capture all the outcomes, and you may be surprised by the real outcome, although you have considered a best, worst, and average case. However, you can model risk and quickly quantify the full range of possible outcomes. Risk analysis helps recognize the difference between the expected value of a decision alternative and the payoff that may actually occur. This tool allows you to graphically show the range of possible outcomes and very often reveals other valuable insights to you, to your management, and stakeholders. In fact, we have seen over and over that risk analysis skills are a career enhancer for our users for several reasons. First of all, you see that as we perform further analysis by doing sensitivity analysis, you will get a good sense for what factors really matter in these business situations with uncertainty. If you are negotiating with another party and you have done your homework with risk analysis and they haven't, you have just given yourself a significant competitive advantage. And finally, as you rise in the ranks of a company, the decisions start to involve more and more uncertainty, and so the skills involved in coping with uncertainty and modeling it realistically become more and more important. Today, we explore how risk analysis and Monte Carlo simulation can benefit you in solving your business problems in uncertain situations, and how easy it is to use Frontline Systems tools such as Risk Solver Pro or Risk Solver Platform to model and manage those problems. Together, we'll review typical applications including inventory management with uncertain demand, manufacturing with uncertain processing times, and revenue management application in an airline with uncertain number of no-shows. Then we'll discuss decision trees and using simulation optimization to optimize your decisions under risk. Before looking at some examples using our Risk Solver products, let's review some helpful information about Monte Carlo simulation and discuss what it is. Monte Carlo simulation is a flexible technique for modeling a real system in which uncertainty is a key factor. It uses repeated random sampling to represent uncertainty. With appropriate sampling, outputs are representative of results from all possible combinations of uncertain inputs. For a given decision, which are values of inputs under your control, simulation describes the outcomes and the possibilities that these outcomes will occur. Now it is time to dive in and see how we can use Monte Carlo simulation in practice. One of the key decisions in manufacturing, retail, and some service industry businesses is how much inventory to keep on hand, making sure you can come through on the promises to your customers. In general, we need to have a dedicated balance between three classes of costs: ordering, holding, and shortage or lost opportunity costs. So let's find out in this example how simulation can be used to understand the range of possible outcomes for total costs. Let's review the Excel workbook, which is ready for our quick review. So this is the Risk Solver Pro ribbon. Let's walk through the tool and some of the features that we will be using today. So anytime you install one of our products, after installation, the program will be loaded as an add-in in Excel and you will see the ribbon appear. Clicking on this Model tab displays or hides this task pane. Simulation Model tab allows you to set up your simulation models. You can click on Distribution button to access a range of predefined probability distributions. Or you can click on Correlations, different correlations between your variables. Or the Results button, allowing you to compute statistics. You can select Output to designate a cell as uncertain function and record over the simulation trials. You can access risk measures, range values, and Six Sigma measures for your uncertain functions. Parameters tab provides the options to run multiple parameterized simulations, and we will be practicing that today. Solve Action tab allows you to run simulation models. Here on the Analysis tab, you can analyze the results, creating reports and charts. Tools tab enables you to create decision trees, fit distributions, and examine your simulation results. This Publish button allows you to publish your models for use and distribution on the web, and you can use the free Risk Solver app. Then you can use this Options button to set options for simulation charts and graphs. Let's explore the Help tab. Here you can display online help, open examples, or an online tutorial, or user guide, access user guide and reference guides, and check your license status and more. Now the task pane. Model tab allows you to view the model in outline form and optionally edit model elements in place. You can see you have simulation. You can see different components of a simulation model that you have. And if you select one of them, you can edit it down here. Let's click on Platform tab next. Here you can view or change the platform options, such as the number of simulations to run, or trials per simulation, and so on. Next is Engine tab. Here you can review and select simulation options for Risk Solver engine. For example, sampling method or random number generation method. You can set a seed and so on. And then the Output tab allows you to view a log of simulation messages. Now onto our example. In this model, we have a beginning inventory at the beginning of first week. The weekly demand for our product is uncertain, and here we have used the Poisson distribution for estimating demand. Let's double click on this cell. Here is the uncertain variable dialog. You can see this is the PDF tab. Then we have the CDF tab which displays a chart of the cumulative form of the distribution function. And then we have the reverse. In the right side drop-down menu in the right pane shows various parameters that you can adjust. For example, let's check statistics that provides summary statistics. There is a percentiles view, and then you can change the chart settings and so on. Okay, here are some of the other problems assumptions. The order quantity and reorder point. You may receive shipment and we face a 2-week delivery lead time. We have a fixed order quantity size, and then the ending inventory of this week would be the beginning inventory of next week. Down below here, we calculate the holding cost, the order cost, and then loss opportunity cost, and here we calculate all the costs in Q14. Now let's just run one simulation. So let's click on simulate, run once. We just ran 1,000 Monte Carlo trials, where on each trial we have a differently randomly sampled value for demand for every week. Then we calculated total cost of inventory. This frequency chart shows the distribution of all possible outcomes for our total costs. This shows us what happens for a specific policy of order quantity and reorder point. We could change this and rerun the simulation to see if there's a better outcome. Let me quickly walk you through the tabs. So we have the frequency chart. You can see what is the mean, about $4,000. You can see the minimum, maximum range, and so on. Then we have the cumulative frequency, the reverse. Then the sensitivity tab displays a tornado chart showing you which input has the most impact on the total cost. And then you can also verify the scatter plot tab. We just looked at a typical Monte Carlo simulation application. Now let's review a summary of how to use this method. To apply the Monte Carlo method, you can construct a mathematical model that simulates a real situation. To do this, you can start with building an ordinary what-if spreadsheet model, as you have always done. Then you need to identify your uncertain inputs and specify probability distributions for them using our tools. Then you need to select outputs to record over the simulation trials. And finally, you have to execute simulation for a number of trials and analyze the outputs. Let's practice this together in a small parts manufacturing example. A machine component is to be manufactured at a production shop. It requires two different processes, drilling and grinding, which are uncertain. The goal is to calculate the number of components that could be manufactured in a workday consisting of 8 hours. Here is the workbook with an ordinary what-if spreadsheet model. You can see in the Model tab to verify there is nothing defined under the Simulation tab. The inputs are the processing times, the drilling time, and the grinding time, and I just use constants here, 2 minutes and 4 minutes. In cell C5, I calculate the total processing time, just adding them. Then In C6, I calculate total time available by multiplying the total processing time by the 8 hours of a workday. And then here we calculate total number of components produced, which is total time available divided by total processing time, and we're rounding it. So our uncertain inputs are the processing times for drilling and grinding. Furthermore, we know that processing time for drilling is normally distributed, and it is with a mean of 2 minutes and a standard deviation of 4 minutes. The processing time for grinding follows a log-logistic distribution with parameters 4, 4, and 5 minutes. You might be wondering how to choose the right distribution to represent uncertain inputs. In the next example, we will look into how our tools can help you do that. And our output is total number of components produced, for which we would like to record the simulation trials. Now we need to define this model and share this information with Risk Solver. First, to define a normal distribution for drilling, let's select cell C2, then click on Distributions, Common, and choose Normal. We can enter the mean of 2 minutes in the right pane. You can see the under parameters. So let's enter mean 2 minutes, or you could have these values in another cell and just use this button to refer to them. And then the standard deviation is 4 minutes. Let me increase the size. As you can see, this distribution can take negative values. Remember that the processing times can never be less than 0. So here we have to make some adjustments. There is an option here to set a lower cutoff value. You can see it is set to -infinity. I'm going to change it from -infinity to 0. You can immediately notice that all negative samples in the chart are rescaled to lie within our desired positive range. There is another option here to censor the bounds. And the difference is that when you use that, samples that lie below the lower bound are set equal to the lower bound. And for example, here if I set it to 0, you can see that causes buildup of probability mass at the bounds, here at 0. So let's remove this. We are just using the lower cutoff. Okay, so let's click on Save. And now if I hover over this cell, you can see that we have a normal distribution in cell C2. And if you check the formula, you can see there is this side truncate function to restrict the drilling time to be always greater than 0, which is one of our function arguments now. Next, for grinding processing time, so we want to use the log logistic for our grinding time. Select cell C3 and then click on Distributions. Let's click on Exotic and then Log Logistic. Now we need to enter the parameters, which are parameter location, which is 4 minutes, scale, which is 4 minutes, and the shape is 5 minutes. Okay, let's click on Save to have the side log logistic in cell C3 for our grinding processing time. So far, we have identified our uncertain inputs and specified probability distributions for them using our tools. Next, we need to select the outputs to record the simulation trials over that output. So the total number of components produced in a day is computed in cell C8, To keep track of the full range of trial values for cell C8 during a simulation, and to get the frequency and sensitivity charts, statistics and percentiles for it on demand, we need to designate it as an uncertain function. To do this, select the cell, highlight it, go to Results, Output, In Cell. You can see that this makes it as an uncertain function without calculating any summary statistic for it on the worksheet. And to verify that we did everything correctly, you can always refer to Model tab of task pane. You can see C2, C3. They are here, our uncertain inputs, and then our uncertain function is cell C8. Now we are ready to run one simulation. And you can see the trials are 1,000. Let's click on Simulate, Run Once. Here are the results, the histogram of the number of components produced. This shows that the total components produced ranges from a low of about 19 to a high of about 76. I'm just reading the minimum maximum values in the statistics, with a mean value of about 41 components. Okay, let's close this one. Here is just another version of this example. I've added more details. Let's review it quickly together. So processing time are just the same. The number of components produced is our output, but if you look here, I don't have that psi output here, and there's another way we can do that. I'm going to show you how. So again, we are calculating total number of components manufactured, and then in C9, we calculate the average number of components manufactured using a summary statistic. Here it is called the psi-mean function. Just it calculates the average. Instead of making C8, which was the number of components produced, as output, this is another way to tell risk solver to recognize C8 as an uncertain function and to keep track of the full range of trial values for C8 during a simulation. Similarly, here we calculate the standard deviation of number of components produced in a day using the psi standard deviation function of cell C8, which is the number of components. If we would like to know the chance of producing at least 50 components in a day, we can calculate this using the psi target function, which we have here in cell C11. So let's run one simulation and see the outcome for these cells. Going to minimize the chart, and then you can see the values. The chance of producing 50 or more components is about 19.6%. And then the standard deviation, and then you can see the average, which is about 41. That was the same as in the chart. And another thing about our products is that you can see here, instead of this cell reference for this chart, we can see number of components where it's a name range. So basically, you would select the cell and just add a name, and then our tool would recognize that. So you can see even here, you can see instead of saying cell C8 for total number of components produced, you can see the name range, number of components produced. Now, let's look at another application. This is an airline revenue management example. Here, we will review some advanced features such as interactive simulation, parametric simulation, and after reviewing the decision tree, we will return to the example and use the power of optimization still with the simulation component. So, there are people that have tickets on a flight and will not show up, and they like to reuse those tickets on a subsequent flight. So there is always an incentive for airlines to overbook a flight. Here we are looking to understand the range of possible outcomes for total revenue given what can happen with no-shows. Let's review the model in Excel. This flight has 100 seats and tickets are $200 per seat. You can see the assumptions for overbooking compensations and no-show refund. The uncertain quantity in this model is the number of no-shows. So we should model this with an uncertain variable. In C7, we are estimating this number and then we are rounding it in cell C6 because it represents the number of people. If we double click on C7, you can see the distribution. It's a log normal with different parameters, and we're going to discuss that in more detail in a few seconds. In cell C15, we calculate total revenue. And then in C16, we use the SIMIN function to calculate the expected total revenue. So we have our flight capacity is 100 seats, and you can see we are selling 100 tickets. So there is no overbooking, and you can see number of overbooked tickets is just 0. But you can see, for example, number of customers showing up here is 92 based on estimating value for number of no-shows. So here we have a distribution for number of no-shows. You might be wondering, how would we arrive at an appropriate distribution for number of no-shows? For an airline, we may have some historical data. This might apply to your business situation as well. Here is the historical data on the number of no-shows from different occurrences of this flight. 21 people, 20 people, 13, 7. We are now going to fit an analytical distribution to this historical data. If you are not sure what distribution to use, you can use Distribution Wizard to help you choose an analytic distribution that fits the historical data. And you can access it from Distribution Wizard. Distribution Wizard can also guide you through the steps of choosing a probability distribution to represent a source of uncertainty. By asking questions when you don't have historical data, this wizard narrows down choices from over 50 to just a handful and helps to establish bounds and other properties of the distribution. So let's select the data. Now click on Distributions, Distribution Wizard. Let's see what this dialog says. Do we have some historical or observed data for this uncertain variable? Let's assume we don't, and let's say no, and click on Next. Here, if we click on More Idea, we get some guidance, and it is pointing us to use consult the literature for your industry to find examples of applications like yours or simulation models were built. Find out by contacting authors what kind of distribution were used for uncertain variables. If you cannot find reports on industry-specific applications, consult the publication of professional societies like Informs, where simulation applications are reported. And give some other, there's another conference, Winter Simulation Conference. Or go to our reference guide chapter, Psi functions, references, and read the descriptions of different distribution functions and decide which one would help you. Let's click on Next. Then this step is to determine whether to use a discrete or continuous form, and then you can also click on More Ideas to better understand which one to choose. And if there are a small number of possible values for the uncertain variable, or if underlying physical process involves discrete, countable entities such as the number of customers arriving at a service window, you can use a discrete distribution. If your data takes on highly fractional values such as most prices, volumes, interest rates, etc., we can use a continuous distribution, and so on. So this is how distribution wizard can help you narrow down to a proper distribution to represent your uncertain variables. So let's click back and change the answer to yes, since we have historical data for different occurrences of this flight for number of no-shows. So now we need to enter or select a range of cells containing the values. I already selected them, so this solver Pro automatically identifies the range of observations. And let's click on next. Again, it is asking if our data is continuous or discrete. Let's choose continuous, and I'm just going to override the selection for illustration. Then let's click on next. Here we have different options that would be to fit the data using an analytical distribution. You can use all of the data using a SIP function or resample the data during the simulation process using SciDisUniform function. So let's keep fit the data to fit an analytical distribution, and let's click on next. You can see the fit option dialog appears. Please note that there is also this fit button on the ribbon menu. So if you didn't need to go through all the process, you can just directly click on fit on the ribbon. Let's override the selection to continuous. Now when I click on fit, Risk Solver computes and displays a ranked list of candidate fitted distributions. Here's the list. Again, a ranked set of candidate distributions that fit this data. You can see that it has chosen the psi-log normal distribution, and that is the best fit to historical data, and this distribution has a mean of about 10 tickets and standard deviation is about 6 tickets. So out of 100 tickets that we sell, we have a mean of about 10 tickets of number of no-shows, and standard deviation is about 6. This is based on the number of tickets sold. Again, we are not overbooking. Capacity 100, we are selling 100, and no number of overbooked is just 0. In a minute, we are going to change that and allow more tickets to be sold. So what does that mean for the number of no-shows? If you think about it, as we sell more than 100 tickets, then we will expect the number of no-shows to go up as well. So we won't use this fitted distribution as is. Instead, we want to create a distribution that depends on the number of tickets sold, and that is what we have done here on the spreadsheet. So remember, this is log normal, and you have the mean about 10, standard deviation about 6. I'm going to close this. Do we wish to accept that fitted distribution? No. Let's double click on cell C7. In the right side, you can see that, let me move it here. Okay. The mean that we have used is 10% of cell C11, which is number of tickets sold. And standard deviation is 6% of the number of tickets sold. Now this provides us with a good model for this business situation. Now let's run one simulation, run once. And here are the results. And you can see the expected revenue is $19,000. You can again see it here too. Now, it is natural to ask how sensitive the total expected revenue is to the changes in number of tickets sold. To answer this question, Risk Solver has a capability to allow us to ask what if, and run a new simulation on each change. To turn on this feature, which is called interactive simulation, simply click on this light bulb on the ribbon. It will light up, and very quickly your first Monte Carlo simulation is completed. 1,000 Monte Carlo trials, the default number, will be executed each time we change the spreadsheet. Now we can play what if with the simulation model we have. Just before that, let me show you how we can put a marker on the chart to have a reference point. To add a marker, click on the drop-down menu, choose Markers tab in the right pane, then click on this plus button, double plus button. We can have a marker at the $19,000 point. I'm going to change the color to red and click Apply. Okay. Now, I'm going to manually change the value in cell C11, which is number of tickets sold, trying to sell more tickets, and the chart will get updated, and we can see the range of outcome for our total revenue. And we are going to sell 110 tickets. You can see the chart will get updated, and the results show that the expected revenue in cell C16 went up. It was 19,000, now it's more than 2,000. So on average, the balance between overbooking compensations and number of no-shows is working toward our favor. Our flight has 100 capacity, we are selling 110 tickets, and we are making more money. Now let's change the number of trials from 1,000 to 10,000. You can easily do it from the ribbon. 10,000 Monte Carlo simulation trials will be done each time we change the spreadsheet. So let's try selling 120 tickets. And here are the results. Well, looks like the expected revenue might have gone up. Now it is hard to tell if we have gone too far with 120 tickets. But let's try 130 and see the results, or maybe 140. Therefore, if you are seeking insights about what matters in this model, interactive simulation lets you explore that much the same way as an ordinary what-if spreadsheet. You can ask what if with uncertainty, just like in the spreadsheet, and you are getting a new simulation every time you change the spreadsheet, where each trial is a recalculation of the spreadsheet. Well, imagine we have done interactive simulation enough times to get used to the model, but now we would like to automate that, so we don't need to sit there and change the parameters ourselves each time. What we can do is to use parametric simulation techniques. Let's turn off the interactive simulation by clicking on the light bulb. Let's close this chart. To do this, you need to select the number of tickets sold and define it as your simulation parameters. So select the cell, click on Parameters, and then Simulation. To change it from 100 to 150, for example, we enter 100 in the lower bound and 150 for the upper bound. So we are trying to change the number of tickets sold from 100 to 150. Let's click OK, and you can see that size in param is added here, and you can also verify that in the Model tab under Parameters. To run a simulation once for each value of the parameter we wish to test, we need to change the number of simulations. So click on Platform tab in the Simulation Model group. First option is number of simulation, which is set to 1. Since we want to test all possible values of the tickets sold between 100 and 150, we can set the number of simulations to 51. With 51 simulations, we are going to run a simulation for 100 tickets, another one for 101, all the way to 150. And then each simulation will be 10,000 Monte Carlo trials, since we just changed the number of trials from 1,000 to 10,000. So when we run this, we will be running 510,000 Monte Carlo trials. Let's click on Model tab. Let me actually clear the output report with clicking on this button, and you can see what would happen when I run this simulation. So I'm just double checking that interactive simulation is turned off. Let's click on Simulate, run once. You can see the output of simulation going from 1 to 51, and it shows that we have 10,000 successful trials and 0 error trials. Now, we are looking at a frequency chart for simulation number 51, but we can look at each individual simulation results by easily changing the simulation drop-down selection in this chart and review frequency chart, for example, for simulation number 18 or simulation number 2. So the worksheet will initially display values for the last simulation performed. Go to this drop-down with simulation index. You can see you can change it to second simulation or simulation number 28, and then with trial arrows we can cycle through individual Monte Carlo trials. So we can go from simulation 1, from 1 to 51, from 1 to 10,000 for each of the simulations, because we have 10,000 trials. So this is how we can change things on the spreadsheet. Also, we can look at all the simulations together using one of several reports or charts. Let's explore the charts. For example, if we want to see how the results varies across all 51 simulations, we can use a trend chart. Click on Charts, Multiple Simulations, and then Trend. Click on the, in this dialog, click on the first button to select all 51 simulations, and then let's click OK. Then Risk Solver then draws this trend chart showing the behavior of our total revenue across all 51 simulations. You can see the value for our parameter, which is the number of tickets sold, on the x coordinate, and then the blue line is the mean value of revenue. Then we can see the 75 percentile and 90 percentile, and we can see that as we sell more tickets overbooking our flight, our revenue goes up, but eventually it peaks out because we are paying too much in overbooking compensations. So we can get some insight right now, and we can see the best number of tickets to sell is somewhere around 116, 117 tickets. Let's leave this example at this point, and we are going to return to it after reviewing the decision trees. So I'm going to close this chart. This is just a summary of steps to apply the Monte Carlo method. Again, start with constructing your ordinary what-if spreadsheet model. Then you need to identify uncertain input and specify probability distribution. Then select the output to record the simulation trials. And there are two ways to do that. You can either select result statistics like SIMIN, or you can without calculating any summary statistic, you can highlight the cell and then select results output in cell. Then execute simulation for a number of trials and analyze the outputs. Now on to our next topic, decision trees. If you are faced with multiple stage decisions and uncertain outcomes at each stage, decision tree is the right choice for you to develop an optimal strategy. The detailed steps on building a decision tree is available in the user guide, and therefore we're going to skip it now and review an advanced application of decision tree in various scenarios. The goal here is simply for you to see different features that are available and the analysis that one needs to consider in a typical real-world application. So Don't concern yourself with details. I will point you to where you can find this example and others, and we're going to review them today, that location, by end of the webinar. So let's click on, this is the example we're going to review. This is about a firm owner considering whether or not to apply for an $85,000 research grant by submitting a proposal. So let's open the tree together. I'm going to click on Help, Examples. Here I'm going to choose Decision Tree Examples, and the example we're going to review together is Grant Decision Analysis. Okay. Let me increase the size of tree for you. So this is the decision tree that we have. First thing I want to do is to highlight the best decision strategy, and that is very easy. Click on Decision Tree, Highlight, Highlight Best. So the first decision node is whether or not to submit the proposal, and that submitting the proposal will cost $5,000. If the proposal is submitted, then we encounter an event node showing a 50% chance of receiving the grant and a 50% chance of not receiving the grant, leading to a net loss of $5,000. If he is awarded the grant, he would then need to decide which technology to use, microwave, cellular, or infrared communication technology. Then he has to spend money in research and development, and he doesn't know exactly what the R&D costs will be. Therefore, each of the three technology options has an event node representing the best case with the lowest and worst case with the highest R&D costs that might be incurred. So according to this best strategy, he should submit a proposal because the expected value of his decision is $13,500, and the expected value of not submitting a proposal is 0. This also indicates that if he received a grant, he should pursue the infrared communication technology because the expected value of this decision, $32,000, is larger than the expected value for other technologies, $29,000 and $28,000. So the optimal strategy is to submit a proposal and use the infrared technology. Now, before implementing the optimal decision to submit a grant proposal as suggested by this analysis, it would be wise to consider how sensitive the recommended decision is to changes in values in the decision tree. For example, he assumed a 50-50 chance of receiving the grant. What if only a 30, 20, or 10% chance exists of receiving the grant? Should he submit the proposal or not? So in the next worksheet, using a strategy table, we're using an Excel data table to analyze how the optimal decision strategy changes in response to two simultaneous changes in the probability estimates. Let me increase the size. What we're doing here is essentially sensitivity analysis on the decision tree and on the decision choices we would make, and so we have created this strategy table but just using the standard Excel data table. In W16 we have this if function formula essentially saying if our decision to submit a proposal is yes, then we should choose the base choice and then capture that value in K27, and then you can see that the array, table function is array entered. So this strategy table makes it clear that this solution is relatively insensitive to changes in the probability of receiving the grant. You can see it stays in infrared communication technology. However, if the probability of encountering high infrared R&D costs increases, the preferred strategy quickly switches to cellular technology alternative. Therefore, the decision maker might want to give closer attention to the risks of encountering high infrared R&D costs before implementing this strategy. Now, instead of simply varying parameters, we can use the power of simulation in our decision trees to consider many more possibilities. So in the next example, which is another advanced version of this tree, we have used the power of simulation. The main changes with this tree are that we have added numerous distributions, both for the probabilities of certain events happening as well as costs associated with certain outcomes. You can see the different uncertain inputs that we have defined. And then we have built this table using several different psi functions. And that allows us to better understand the decision with the highest overall expected value, as well as a way to look at results by individual trials. So let's run one simulation. And we are going to focus on AA16. So I'm just going to select that output function, uncertain function. So this is a frequency of choice of one of the 4 strategies related to cell AA16. Again, these are available to you, and you can just really verify them in detail later. There are 4 decision alternatives, and we have numbered them 1 through 4. Here you can see that while strategy 2 overall have the highest expected value, that was only the case across about 1/3 of the trials. Fairly close behind it was strategy 3. This tells us it may be worth looking into the distribution of results across each strategy to see if we are actually more comfortable with another strategy given potential downside in some outcomes. Okay, let's close this. Okay, and let's go back to our slides. Now on to our last topic for today. This is about how you can make best possible decisions in situations where you have risk and uncertainty. Here we'll use optimization capabilities. So in these types of problems, we have uncertain variables. You can determine them with asking what external factors are not under your control. For example, number of no-shows, that is our external factor. We will also have decision variables, and we can determine them by asking what factors are under our control, like how many tickets to sell. This is under our control. The next component is the objective function. We want to maximize our expected revenue, for example. You can determine objective with asking what measure are we trying to optimize. And typically you have constraints, and you can determine them by asking what restrictions limit our choice of decision variables. Now let's go back to our airline revenue management model. Let's turn it into an optimization model, still with the simulation. So we are using Risk Solver Pro. And now we need to use optimization capabilities. So we have to change the product to access the optimization features. Let me show you how you can do this. Click on Help, Change Product. Instead of Risk Solver Pro, you're going to choose Risk Solver Platform and click OK. Now this product will allow us to perform conventional optimization, Monte Carlo simulation, and simulation optimization, and much more, which we'll talk about in a few minutes. So you can always do this when you have a free trial. So you can see we have the simulation model components, and now we have the optimization model components, our decision variables, constraints, and our objective, and some other features. So let's first define the number of tickets sold as our decision variable. This is what we have the control over. So first thing I need to do is to remove this formula from the cell that I want to define as my decision variable. So let's click Enter 100. So there should not be a formula in the cell that you want to select as your decision variable. And also another thing we need to do is to put the number of simulations back to 1. You can see now we have the optimization model options added here. So to define number of tickets sold as our decision variables, select C11 on the worksheet. Now click on Decision button, and you will see that under Optimization, we have Objective Variable and Constraints. Under Variables, we have C11. This is how you can verify that you have correctly defined your decision variable. So we have this normal decision variable now. Now we want to maximize our expected value of total revenue, the average value across all the simulations. So to define C16, the expected revenue as our objective function to be maximized, let's select it and then click on Objective and then Maximize Normal. You can see under Objective we have C16 to be maximized. Okay, we are ready. We have a simulation optimization model. Let's click on Optimize. So this is guided mode. This is a step-by-step help for your modeling efforts during optimization. It gives you some information about your model structure, and then it tells you what has happened with your solution. So Solver found this solution for us. As we explored alternatives in the optimization, we decided that we should sell about 117 tickets. This is consistent with our parametric simulation trend chart, where that reflects the balance between no-shows and overbookings, where we can earn the most revenue, which is in average, it is our average revenue is about $20,619. This was an example of simulation optimization. You can do much more using our tools when you want to optimize on certain situations, and you can refer to our user guide to explore the stochastic optimization chapter. Also, I will show you the link to our YouTube channel, and I posted a couple of videos on stochastic optimization that you can use. Now for a few important points regarding the paybacks of risk analysis. Monte Carlo simulation helps you evaluate the impact of uncertainty in a business situation. The simulation approach is more realistic than give me a single number, with the goal of identifying the best decision involving multiple stage decisions and uncertain outcomes at each stage. Decision tree helps you develop an optimal strategy. This is much better than ad hoc decisions as you go. And simulation optimization helps you determine the best way to allocate resources in the presence of uncertainty. This will allow you to save money while hedging for risk. Just a brief discussion on our product line. During this session, we started with Risk Solver Pro and then Risk Solver Platform. We showed what you can do with a Risk Solver Platform for simulation optimization. These are professional level products, and we have much more. You can upgrade to Analytics Solver Platform, for example. Our Risk Solver products are by far the fastest Monte Carlo simulation products in Excel, often 10 times faster than competitor products. This matters when you are performing advanced analysis, such as multiple parameterized simulations or simulation optimization or what-if analysis with interactive simulation as we practice today. This is still talking about simulation and decision trees. Frontline whole product line contains a much broader area of analytics, so let me show you the full picture. It includes forecasting, text mining, data mining, simulation and risk analysis, decision trees, and conventional and stochastic optimization. An analytics Solver platform is a complete toolset for descriptive, predictive, and prescriptive analytics for problems of any scale. This wide-ranging product line empowers you to perform analytics on the web and desktop spreadsheets, also web, server, and desktop applications in any scale. Now, if you're asking what is the next best Step to begin. Please register at our website for free. This allows you to access simulation tutorials, our downloadable user guides, example models like the ones we have been showing here today. Furthermore, it allows you to download a free trial at any time whenever you're ready. Try it yourself, go to example models after installation, and during this trial period you have full technical support. You can ask questions, just give us a call, use live chat, or send us an email. Thank you very much. Let me share the link for our YouTube channel. So I'm going to share it in the chat box. YouTube Frontline Solvers, click on playlists. You can access the webinar recordings here, and then if you're interested to learn more about stochastic optimization, here are the list of videos in the playlist for stochastic optimization, features of risk solver products. So I'm going to share this link with you. Let me send it to all. Please remember, you are welcome to send any questions or comments to my email address, consulting@solver.com, and I'm going to share it with you here, consulting@solver.com. Okay, now it is time for Q&A. Again, thank you very much. I really enjoyed presenting this webinar to you and trust that it was helpful to you. Okay, we look forward to future webinars with you. If you would like, join me tomorrow for the data mining webinar. We appreciate your time. Bye for now.